So last week actually on Monday, right? Monday we discussed about the slip frequency and also the rotor speed and the stator speed. So these are not of the so-called relativity between the stator and rotor. So I wasn't explaining really well. So today I try to do more notes so that you can able to tell you a bit more. So firstly, we started off, we have a single phase. We said the single phase not quite working because the symmetry of the rotating field is not doing really well. We can only see 2 poles. We gradually move on to 4 poles, so that will be more realistic. The rotating field generated by the 4 pole look more symmetrical. So usually the performance will be much better too. And then we progress to 3 phase. In this case, we're able to produce totally in here, although 2 poles multiplied by 3 becomes 6. We're able to have much better distribution. And then so on, we have 4 pole, 3 phase, and then even though it's 6 pole and 3 phases. So that's the comment. We can see that 2 pole usually have high pole, and then we prefer high pole because actually the motor speed, we don't need to be that high anyway. And then we have more pole, we have lower speed for the motor. And then there's some equation. You can see that how the number of poles relate to the base frequency of the rotor we're going to see. And then we also discuss about rotating field. So how the sinusoidal variation of the three-phase voltage, each one displayed by 120 degrees, we're able to create the rotating field. So that means we can see that if it's standing in here in the air gap, we're able to see the rotating field look like more rotating. And then we also discuss about why the rotor squirrel cage, mainly the structure of the rotor will be like that. And then hence we can therefore look like the rotor actually had the short circuit only equal to 1 turn. So later on when we discuss about the rotor, then we can able to understand more about how the rotor circuit look like. So the rotor, we can see that there will be a bar with a conductor, only a 1 turn, have an end ring to short circuit with them. Inside the rotor, we have lamination core, which is able to stop all the eddy current inside the core. And one thing we like to use the magnetic core because we want to create a low reluctant path for the magnetics. So in this case, all the stator thrust we're able to penetrate through the rotor rather than go through other directions. So that's why low reluctant path for all the rotor will be important in the center. So here are this discussion between the induction motor and DC motor. So usually squirrel cage will be the ring we have been using quite some time. We prefer this one. Mainly will be we don't have any physical contact in the rotor to external circuitry. But however, DC motor, we don't have that problem. And also that's why the maintenance for induction motor will be much lower as compared to the conventional DC motor, which we have to use carbon brushes and also commutator. And the speed control as well, this motor will be much better. And however, in this motor, we are now progressing because we do have some new technology using vector control to further improve that. Then for the operation, we need to go through all these equations, which could be quite useful. For instance, the slip ratio, sometimes we call it slip, is the difference between the synchronous frequency of the motor subtracted with the rotation speed of the motor, which is the rotor speed, and divided by the base. And then we also go through a few equations of this, including the rotation speed. Actually, we arrange them equal to synchronous speed, and then multiply by 1 minus s. S is just a ratio, a percentage, how much the rotor deviates from the synchronous speed. So when a motor is rotating, usually they will slow down a little bit, only just a few percent. And then we can also see that there's also F2 frequency, and which is the induced voltage of current in the rotor circuitry. So which actually will be much lower frequency. Last time we mentioned to you that frequency usually only just a few hertz because that is the frequency appear inside the rotor, not appear in the stator. The rotor has been rotating, so the actual frequency you can see from the rotor is actually much lower. So we can see that the frequency, low frequency, only just a few hertz. So that's why we don't care too much about eddy current in the rotor because they are running at low frequencies. So we also mentioned about the voltage. the voltage mainly about the similar to a transformer equal to turns ratio. Stator and rotor also have a transformer turn ratio relationship, which is M1 over N2. But we also see that there's another relationship due to the induction, which will be based on the slip. So this equation are derived from how the voltage being induced between the stator and rotor, and that's a relationship of the slip. So that's to say the induced voltage from the stator to the rotor have a slip ratio. Actually, this voltage is quite small because usually S is quite small. So the apparent voltage inside the rotor will be much smaller. Later on, you can see a tutorial about that. So we also discussed about a tutorial example how a voltage 460 volt motor, four pole and three-phase motor look like. So usually 460 volt, if you don't mention anything, that must be the line voltage. And then we see that the slip will be 0.05. So we're going to calculate the synchronous speed and the motor speed. You see synchronous speed is when the motor becomes synchronous. So that speed actually would equal to the input frequency 60 Hz divided by the pole pair, because the electrical frequency is 60, but the mechanical frequency, every cycle, they only pass through 2 poles. So now I have 4 poles. So the synchronous frequency, the rotational speed for the motor will be divided by the pole pair. That means if 4 pole, we divide by 2. If 6 pole, we also divide by pole pair 2. So in this case, will be 1,800. So 1,800 is the base frequency for the mechanical rotation. So that's the maximum speed you are able to achieve. So that means you can see that the speed will be much slightly lower by the pole pair. So that's to say the motor speed slightly less than the synchronous speed. So that's the maximum speed you're able to achieve by the input frequencies, which 1,800, because the motor running slightly less than that. So that percentage called the 0.05 will be only reduced by 0.05 this ratio. So that means the rotor speed or the motor speed will be equal to 1710. So rotor speed, or we can also call the rotor speed, they're the same. Let me talk about that. And then we also see the air gap field. You see, when we energize the motor, then we have 60 Hz energized to the winding. That each time this electrical cycle only pass through 2 poles, and then next will be another 2 poles. So that's to say the air gap field will just rotating not 3,600, but only rotating half of them. So that means you can see that the air gap field, the speed of rotation is only 1,800 because of the pole arrangement. You can, if the question change into 2 poles, then the air gap speed will become 3,600. So they all reduce it according to the speed and also according to the pole pair. And then the slip in so whenever talking about RPM, that means the mechanical rotation, not electrical. So the mechanical rotation, you can see that we now have 1,800. That's the base, and then the slip means how much it being reduced. Then that's why we get 90 RPM. So that's mechanical slip. What's the difference between the synchronous and the rotor movement? And then next, we try to see the correlation between the rotor field to different structure. Firstly, we like to see what's the rotor field we mean. The rotor field, we have the stator field generated by input voltage, right? And then energized on the coil become the stator field. The stator field look like rotating because when we sinusoidal move, then that will continue to move together with the input voltage. So that's why I say the stator field, or so-called the rotating field, will be the same frequency as the input, but however, with the pole pair relationship, then will be reduced by 2. But that field will penetrate through the air gap to the rotor. So the rotor will experience the same kind of the field too. So later on, I can see the correlation. Next few slides also create a few new slides to you, so they're able to understand how the rotor field look like. So in here, you can see the stator field penetrate through the air gap and then go to the rotor. The rotor field will feel the same kind of field. So these two fields more look like locking to each other. So the speed of the rotor field will therefore the same as the stator field or the rotating field. So that's to say now we have do that concept. Then we can know that if the rotor field relate to the stator rotating field because they're locking to each other, so that means the relative speed between them will be equal to 0. They are locking to each other anyway. And the next thing to see how the field relate to the rotor structure. Then, because the rotor field is same as the stator rotating field, and then the rotor is now also rotating. The rotor structure, the rotor winding, the rotor rotating at a speed equal to rotor speed. So that's why the rotor field is same as stator, which is 1,800, and the rotor is just rotating slightly slower by the slip, right? So that's why the difference between them is also equal to the slip in RPM. So this mainly means the rotor and the stator different in the speed. That's what you mean. And then next question to say, how about the stator structure? Stator structure is physical item, stationary, just like not moving. And then the rotating field, which is same as the rotor field, are also rotating. Yeah. And because of the pole pair, so it's not rotating at 3,600, only rotating each electrical cycle, rotate by 2 pole pair. So become the speed become halved. So that is to say, you can see that when the rotating field relate to the stator structure, just like halving the speed, become 1,800. So that's how we can see that. So the field concept here will be slightly complicated. I should not put it here because that will confuse you. Since I already put it here, I still need to explain to you all. So this part, probably we can investigate further detail when you go for high level of the class. But for this time, you can able to understand the correlation between the stator field and rotor field, how the relative speed between them. I think that would be quite useful concept. You try to understand them. I'm not quite sure you understand. Do you get it?
I have a couple of questions.
Yeah, please.
My first question is the stator. Why isn't the stator has its own field? So why doesn't it produce its force? Why is that? Why isn't it moving?
The stator is the hardware or external structure. It's fixed to the motor frame, so it's stationary. We pin it to the ground.
Okay.
It's not rotating. So the stator cannot rotate anything. So the stator will energize them. The stator coil are attached to the stator frame. So we energize them with the stator current. So and then from there, you can therefore create the field. I do have another slide to show you later on how the correlation, how one-to-one become another. So you may understand much better using that slide. So continue your question.
Good question. What exactly causes the stator frequency and the rotor frequency to drop off? Is it like due to electromagnetic induction that drops off frequency a little bit, or what is like the phenomenon of that?
That's a really good question. You can see that there's a few things in here. The induction motor are based on the induction. So that means we need to have some rotating field, variating field to induce the EMF in the rotor. How can it induce properly? You see when a stator and rotor are stationary, of course the stator must be stationary. The rotor, when it stands still, before we rotate, it just look like a transformer. Then the induced voltage between them just look like transformer voltage. Right, the next question we mentioned about just look like a transformer voltage. They always be there. And the next thing to appear will be once we start to energize the stator, Then beside we induce voltage through the transformer correlation. Then you can see that the rotating field will induce the EMS on the rotor. The rotor itself will generate the current inside the rotor current. This rotor current will therefore induce its own electromagnetic field around the rotor. So these two fields actually interact to each other, try to opposite each other to force the rotor to rotate. And then you can see that the rotor will rotate, that rotor will try to catch up with the rotating field, but it never can able to catch up exactly. So there will be some lagging behind. That lagging behind will cause so-called the slip. So that's why we have to say a few percent of the slip. The design of this motor is not called the synchronous. We do have another type of machine called the synchronous machine, which we do use a permanent magnet inside, and then external coil will energize step by step. North pole attract the south pole, and next north pole attract to south pole. Then you step by step to synchronize them. Then you're able to make sure the input frequency and stator will synchronize with the magnet inside. That's called a synchronous machine, which is another type of motor. But this motor is called asynchronous. We don't have a PM inside the motor. We only have induction. The induction coil, which is the rotor, you try to build up a water field there. You catch up the external stator field. You always try to catch up, never can catch up exactly. You can see that if you're able to catch up exactly, then it just look like the rotating field from the stator, and the rotor field will equal the same kind of frequency. That in there don't have any variation. We might have a variation changing in order to have a good induction from the rotating field induct to the rotor. So this one, the principle would be that actually we try to drag the rotor to follow the stator, but we don't want them to be same frequency. When they're same frequency, we lose the induction. The same frequency, they move in the same kind of the speed, they have no induction. Yes?
So just making sure when they have the same frequency, is the rotor moving, rotating, right?
Yeah, we do have many chances that with the stator and motor at the same frequency. The thing I say same frequency means the rotating frequency is same as the rotor frequency. If the same frequency, the rotor can still go rotating, but there's a low in induction. Once you do that, you lose our energy in the rotor will slow down, and then you catch up, also at force. So that's continuously doing that. Of course, you won't see that, but they are internally doing that kind of the so-called zigzag movement. So that's why induction is quite special, I should say. Inside the rotor and stator, we do have a kind of the relativity kind of motion. So the principle is really interesting, but it's more complicated than simple DC motor. So that's why I teach DC motor to you first. In this motor, we need quite a few weeks to go through that. So the next question, you can see that induced voltage. We have two induced voltage here. One is simple transformer. One is the slip induction due to the induced voltage to the rotor, which has S relationship. So actually, the machine's rotating. These two should be combined together. Then we have 0.05 times the turns ratio multiplied by the voltage become the voltage appear in the rotor. So this voltage actually quite low voltage. You can see that. Really, really low voltage. You can imagine machine is 100% efficiency. So when the voltage is so low, the current is really, really large. So that why we need to use rotor bar rather than rotor wire to do that. So in this, you can see that we have high current inside rotor to create us with the Lorentz force. The roughly about what that tutorial mean. And then when I go back, I start to think, oh, you should understand the correlation between the rotor field, how the rotor field will come from. So in here we say the rotor field is the magnetic field generated by current flowing in the rotor conductor must be. So where that current come from in the screw cage, Then let's see what happened for the whole thing. So where the rotor field come from? Firstly, we got the stator field coming from the stator. The stator field generates stator voltage, generates stator field, and then we can therefore induce the voltage in the rotor, just like normal transformer induction, the coil coupling induction. And then we do have the induced voltage appear in the rotor. Then, of course, once you got a voltage on the rotor winding, that's why I create a current there. So that's why I create a current there. You see the rotor circuit is closed circuitry, so the current cannot go anywhere. We have no connection outside, only circuit inside those screw cage. So once we got current there, we create the rotor magnetic field. Once the current, automatically create the field. So that's why I can see the field are mainly doing that step-by-step creation. So eventually you can see the stator field and rotor field, they are against each other, can produce you with the rotation. So that's how we understand the induction motor work. And the next thing I like to examine about what kind of frequency will be there. Because we have been thinking about, oh, the rotor frequency is so low. Why the frequency is so low inside? You see, that's a quite important part of the induction motor. I have been taught to many students, even though some graduate students, they're working on power electronics, they don't know the frequency inside the rotor is low frequency. It's quite surprising. So let's explain to you what happened. You see, our rotor had the same frequency as the stator. They all 60 Hz because they lock into each other. The stator field will penetrate through the air gap to the rotor, and then the rotor generates the same kind of field. Actually, they lock into each other. They all become 60 Hz. And anyway, the rotor is mechanically rotating, but the current inside are finally so frequency because the stator frequency locking to the rotor field. And then the rotor is now rotating. They're rotating slightly less speed by the speed percentage, like 5%, lower than the stator field. And then the current inside, because they're locking the current, also producing the rotating, the current inside the rotor producing the rotor field. Since this field, same field is locking, so then the only current inside from the rotor must be the difference between the two frequencies. So that means the stator field here, we got the stator, certain frequency. So this equal to the rotor field, rotor total frequency. But this frequency have two components. One would be the rotor rotation plus its own rotor current. The little current floating inside the rotor. So that's why once the locking appear, the rotor current can only appear to a low frequency, like in this example, 3 Hz. So that's how it look like. So you can see emergence also look like relativity. So because the rotors like merry-go-round inside, you have something waving at 3 Hz. The merry-go-round are doing about 50 something Hz. The external, we can see total frequency will be 60 Hz, but inside two components. One will be the rotor rotation, one with its own current frequency. So that's how we understand. These two frequencies must add together to produce our rotor field frequency. So that's how we understand why the rotor have much lower frequency. So, and then I try to think about how to explain to you properly. So I just think about this method to talk about that. So the rotor only about 3 Hz. And then physically the whole rotor rotating at 1,700 RPM. So the combine of them, so externally you can see the rotor rotating, inside the current only 3 Hz. When I sitting outside the rotor, I can see that they combined together. You can see that the rotor current are summation of two adding together. So that means the rotor speed is 1,710, and then the the rotor field, 3 hertz equivalent to 990. So they combine together will be 1,800. Externally, when I'm sitting outside, it's only the stator rotating field. So locking to the rotor. The rotor itself has a rotor physical movement, but its own current movement. So that's how we see the combination. That concept are really similar to what we see when you sitting on a merry-go-round. Merry-go-round also has something rotating inside the combined frequency. So we did that, and then we do the measurement for the water current. It really is low frequency current. So that means that's how we understand using the merry-go-round principle. So that is similar to just relativity. Just like you are waving, if you're sitting on merry-go-round, you're waving at 90 RPM, the merry-go-round is 1,700. The whole thing, when you observe from outside, you can see that you are waving at summation of two frequency. That when you're waving, that would generate the motor field. That waving means the motor current generate motor field, then that will lock into your external field will be 1,800 RPM. So that's how I try to explain it. Not quite sure if that's the way you do understand, because you have difficulty to imagine how the current field are located inside. You can't, not quite easy to measure it, right? You can only imagine. Any question?
Can you also, I don't know if this is a good analogy, but you know when car tires spin fast enough where it looks like it's not spinning at all, I think that kind of similar to that. You know,
Quick second, what?
it's like when the rims on the car tire, like sometimes,
The first one, I don't get it. Which one?
is that, can you analyze it like that too? Is that or is that a different analogy?
I don't get the question. You say what? Here I try to use merry-go-round to explain the merry-go-round just like the rotor, which is rotating. And the current inside, just like the wave things are flat. The current inside would be say 3 hertz or even the 90 RPM. The merry-go-round is the rotating of the rotor, 1,700. Add together, when you observe from outside, you can see that when you are waving at much higher frequency, summation of two things, the two of them add together. So that's how I explain to you. I don't quite get your comment.
Okay. Yeah, because when you're standing still, it looks the same, right? The speed of the merry-go-round.
When you stand outside the merry-go-round, you can see these two frequencies are adding together. 17, 110, and 90 are adding together. Because it's just two of them are more look like summation of the movement. But that's a way I can interpret that. But for the induction motor, we do a rotor rotation, but the frequency inside the water current also generate in the field. So that's why to add together will become how we understand. In here, this feels like mainly to tell you why the rotor frequency is so low frequency, not 60 hertz, not 30 hertz, but only about 3 hertz in this case. Yeah. That is a kind of the relative motion. So that's to say, the current inside the rotor also create a relative motion due to the rotor rotation. If the rotor is not rotating, then the rotor current will become.
Can you say it again?
No, I say the rotor is now rotating at roughly about 17, 110 RPM, right? Then you can see the current inside is 3 hertz. Now that if you suddenly stop the rotor, then what the frequency inside the rotor? The frequency of current, the electrical current inside the rotor. No. What do you think?
I assume it has to be preserved, so I imagine it would get much higher.
Yeah, much higher. If you stop the rotor, then the whole thing just looks like a simple transformer. Simple transformer, you input 60 hertz from the stator, the rotor secondary side also becomes 60 hertz. Once it starts to rotate, then rotating frequency will add to the rotor frequency, become the input frequency. So these two are locked to each other.
I think I'm confused because we have current frequency or speed frequency and our magnetic field frequency.
That's the problem. There are many people about it. So many when we just try to use two-pole machine, you don't need to worry about the number of pole because electrical frequency is the one applied to the stator winding. But because how you apply them, you have 4 pole. Each time you will apply only travel 180 degrees, and then another 180 degrees, and so on. So that means you actually are using the number of poles to reduce the rotating field you generated. So for instance, the diagram here.
So in your analogy, you just said
Yeah.
the motor frequency would go to 0, but the current would go up because due to
The frequency will go up.
cylinder being
Yeah.
transformed.
Two of them add together become the input frequency. So for instance, when you apply electrically, we only apply one electrical cycle, the field only goes half because the 4-pole machine. When you apply another second cycle, you go another half. So that means when you apply 60 Hertz electrically outside from the stator will experience about half of the frequency because slowed down by this kind of theory. So that's why rotate the base frequency for the motor become 1,800, not 3,600, because we're being half by that mechanical arrangement. We got 4 poles, that's all. Yeah, every time we arrange it, we do this, and then next cycle do this, next cycle do this. So mechanically, you reduce by half. So this concept need to think about anything, any other question? It's quite important concept for induction motor, but you need some time to digest, to think about that. Yeah. But this concept is widely distributed for all the internet. If you go to any internet, million people talk about that. So I got my way to explain to you, but they also have their way to explain to you. There's a million textbook. You can go to the library, you can see so many textbooks. Induction motor has been here for more than 100 years. There must be so many people trying to explain that concept. But there in mind, you can see that the single phase 2-pole machine, you don't need to worry anything about the frequency and the reduced speed, right? But once you go to 4-pole, then the speed will reduce by half, and 6-pole reduce by two-thirds, right? So that's progressively you can see the movement. So get some time for you to think about that, and then to see again. Not quite sure. We try to explain it again. Yeah. So to conclude, you can see that induction motor would be one of the most popular machine we have here. Really large market share, at least 65, maybe even more than that. And the voltage, AC voltage from the stator will generate rotating field. That rotating field interact with the winding to create the motion. So mainly is that we're able to create a rotating field. So the common number of pole could be 2-pole, 4-pole, and 6-pole. So 2-pole, we have the same kind of frequency between the input frequency and the rotating frequency. And the rotor, you can see that this is a closed circuitry, but closed circuits mainly mean screw cage. So we do another type of motor, not closed circuit. So that's why closed circuitry, like this screw cage, would be more popular nowadays. And we do produce a formulation about the induced voltage from the stator to rotor. That will be related to the turns ratio plus the slip. So that's the main thing we try to learn here.